Welcome to today's session. In this problem, we'll explore an exciting challenge titled Maximize Sum of Array After K Negations. Together, we'll break it down, examine various approaches, and work toward an optimal solution. Let's dive in. In this problem, you are given an integer array called nums and a value k. The task is to maximize the sum of the array after performing up to k negation operations. A negation operation allows you to pick any element in the array and change its sign, flipping it from positive to negative or vice versa. For example, if you have the number 4, you can turn it into -4, or if you have the number -3, you can turn it into 3. You are allowed to perform this operation at most k times, and the goal is to maximize the overall sum of the array after applying these operations. To clarify, the input includes the array nums and the integer k, and the output will be a single integer representing the maximum possible sum of the array after making the changes. Let's look at some examples to better understand the concept. In the first example, the input is nums equals 4, 2, 3, and k equals 1. Here, we are allowed to perform only one negation operation. To maximize the sum, we choose to negate the number 2, turning it into -2. The array now becomes 4 minus 2, 3. Adding up the elements of this updated array, we get 4 plus, -2, plus 3, which equals 5. So, the output for this example is 5. Now, in the second example, the input is nums equals 3, minus 1, 0, 2, and k equals 3. This time, we can perform up to 3 negation operations. First, we negate -1 to turn it into 1, so the array becomes 3, 1, 0, 2. Then, we attempt to negate 0, but since negating 0 has no effect, the array remains unchanged. At this stage, we still have one operation left. For the last operation in the second example, we negate the smallest positive element, which is 1, turning it into -1. The array now becomes 3, minus 1, 0, 2. Adding up the elements, the sum is 3 plus, -1, plus 0 plus 2, which equals 6. Therefore, the output for this example is 6. In the third example, the input is nums equals 2, minus 3, minus 1, 5, minus 4, and k equals 2. This time, we are allowed 2 negation operations. First, we choose to negate -4, turning it into 4, which results in the array 2, minus 3, minus 1, 5, 4. Next, we negate -3, turning it into 3, giving us the updated array 2, 3, minus 1, 5, 4. Adding up all the elements, we get 2 plus 3 plus, minus 1, plus 5 plus 4, which equals 13. Thus, the output for this example is 13. To ensure your solution works for all cases, pay attention to the constraints and edge cases. The constraints specify that the array can have up to 10,000 elements, and the values within the array can range between -10,000 and 10,000. Additionally, the number of negations allowed, k, can also go up to 10,000. Some important edge cases to consider include situations where k is very large compared to the number of negative numbers in the array. In such cases, after negating all the negative numbers, any remaining operations will toggle the smallest absolute value repeatedly. If the array contains only positive numbers, the smallest positive number will be negated multiple times if necessary. If the array contains zeros, negating 0 will have no effect on the sum. Finally, if k is 0, no operations are performed, and the sum is simply the sum of the original array. Keep these scenarios in mind while designing your solution. To begin, let's consider the brute force approach. The intuition behind this method is fairly straightforward. We repeatedly find the smallest element in the array and negate it. This process is repeated exactly k times, with the goal of increasing the sum of the array after every negation. The steps are simple. First, we iterate k times. During each iteration, we locate the smallest element, multiply it by -1 to negate it, and then recalculate the sum. However, this approach comes with a major drawback. Finding the minimum element during each iteration takes n, and since we repeat this process k times, the overall time complexity becomes k*n. This makes the brute force method inefficient, especially for larger arrays or when k is large, due to the repeated searching for the minimum element in the array. A more efficient solution is the optimized greedy approach. Here, the key idea is to negate the smallest, or most negative, elements first, as this has the greatest impact on maximizing the sum. Instead of repeatedly searching for the smallest element, we can use a min heap, or priority queue, to organize the array elements. With this approach, the smallest element is always accessible in O log n time. The process involves building a min heap from the array, which takes O n. Then, for k operations, we extract the smallest element, negate it, and push it back into the heap. Once all k operations are performed, the sum of the heap is calculated. This method significantly reduces the time complexity to O n plus k asterisk log n by optimizing the operations required to access and modify the smallest element. The min heap based approach offers several advantages. It is much more efficient than the brute force method, particularly for large arrays or high values of k, as it minimizes redundant computations. By always prioritizing the smallest values, the strategy directly aligns with the goal of maximizing the sum. However, there is a trade-off. Using a heap adds a slight layer of complexity to the implementation. Another alternative to consider is the sorting-based greedy approach. In this method, we first sort the array in non-decreasing order. Once sorted, we can simply iterate through the array and negate the smallest elements up to k times. If there are remaining operations after negating all negative values, we adjust for parity. If k is odd, we negate the smallest absolute value in the array. The sorted array allows for efficient access to the smallest elements, making this approach intuitive and easy to implement. The sorting-based approach has its own set of benefits and trade-offs. Sorting the array takes O n log n, and iterating through it for negations adds an additional O n, resulting in an overall complexity of O n log n. This makes the method efficient for most practical scenarios where sorting is the dominant factor. It is also simpler to implement compared to the heap-based approach, as sorting is a one-time operation. However, this simplicity comes at the cost of reduced flexibility. Unlike the heap-based method, which dynamically adjusts to the smallest values after each operation, the sorting method is less adaptable since it relies on a static ordering of the elements. The chosen strategy for this problem is the optimized greedy approach using a min heap. This method offers the best balance between efficiency and flexibility, with an overall time complexity of O k asterisk log n after the initial heap construction. By prioritizing the smallest values for negation, the min heap approach effectively maximizes the sum while dynamically adapting to the remaining operations. Key observations further justify this choice. Negating the smallest or most negative values has the largest impact on the sum, and any remaining operations after handling negatives must consider parity to ensure the result is as large as possible. While the heap-based method is slightly more complex to implement than sorting, its efficiency makes it ideal for scenarios involving larger arrays or higher values of k, making it the preferred solution for this problem. To solve this problem, we aim to maximize the sum of an integer array after performing up to k negations. A negation simply means flipping the sign of an element, turning a positive number into a negative one or vice versa. The key question is how to strategically choose which elements to negate in order to achieve the largest possible sum. A straightforward, brute force approach involves always targeting the smallest element in the array for negation, as flipping the smallest value typically leads to the maximum immediate increase in the sum. The process begins by initializing the input array and setting a counter, k, to track the number of available negations. This setup allows us to systematically perform the required operations while keeping track of changes to the array and its sum. Now, the brute force approach proceeds with k iterations. In each iteration, we scan the array to find the smallest element. This element is selected because negating the smallest value has the greatest potential to increase the array's total sum. Once we identify this element, we negate it by multiplying it by -1, and then update the array to reflect this change. After completing all k negations, the final step is to calculate the sum of the updated array, which represents the maximum sum achievable under the given constraints. This sum is then returned as the result of the algorithm. Let's walk through an example to see this process in action. Suppose the input array is 2, -3, 4, -1, and k is set to 2. In the first iteration, we identify the smallest element, which is -3. Negating it gives 3, and the updated array becomes 2, 3, 4, -1. In the second iteration, we again find the smallest element, which is now -1. Negating it results in 1, and the updated array becomes 2, 3, 4, 1. Finally, we compute the sum of the updated array, 2 plus 3 plus 4 plus 1, which equals 10. This is the maximum sum achievable with the given input and constraints. The effectiveness of this approach relies on its greedy nature. By always targeting the smallest, and therefore the most negative, value for negation, we ensure the largest possible increase in the array's sum at each step. This local optimization leads to a globally optimal result for this problem. However, certain edge cases need to be considered. If all elements in the array are positive, no negations are needed, and the sum remains unchanged. When k exceeds the number of elements, some elements might be negated multiple times, flipping their signs back and forth. Additionally, negating 0 has no effect, so it should only be considered if no other options exist. To implement this approach, the input array serves as the primary data structure. During each operation, it is updated in place as we negate the smallest element. However, scanning the array to find the smallest element in each iteration can be inefficient, especially for large arrays. A min-heap offers a more optimized solution. In a min-heap, extracting the smallest element is significantly faster, taking only O log n time compared to the O n time required for a linear scan. This optimization reduces the overall time complexity of the algorithm. Speaking of complexity, the brute force approach has a time complexity of O, k asterisk n, where n is the size of the array and k is the number of negations. By using a heap, the complexity improves to O, n plus k asterisk log n, with O, n, for heap construction and O, k asterisk log n, for k extractions and insertions. Space-wise, the brute force approach requires O, 1, extra space, while the heap-based solution uses O, n, to store the heap. The optimized approach using a min-heap begins by constructing the heap from the input array. This ensures that the smallest element is always readily accessible. For each of the k negations, we extract the smallest element from the heap, negate it, and then reinsert it back into the heap to maintain the heap property. Once all k operations are completed, the final step is to compute the sum of all elements in the heap. This sum represents the maximum possible value of the array after the specified number of negations. By leveraging the efficiency of a min-heap, this approach provides a scalable solution even for larger arrays or higher values of k, making it a significant improvement over the brute force method. This solution optimally maximizes the sum of the array after k negations. The algorithm begins by sorting the input array so that negative numbers appear at the front. This ensures that the smallest, most negative, numbers are considered first for negation. Next, we iterate through the array and negate as many negative numbers as possible, up to k times. Each negation decreases the value of k by 1. This step ensures the largest possible increase in the sum of the array. After processing all negative numbers, there may still be remaining negations if k greater than 0. If k is odd, we negate the smallest number in the array. To find the smallest number efficiently, we resort the array and negate the first element. If k is even, no additional operations are needed because negating twice results in no change. Finally, we calculate and return the sum of the modified array. This approach ensures optimal handling of all edge cases, including scenarios where k is very large or the array contains only positive numbers. The algorithm runs in O, n log n, time due to sorting, making it efficient for input sizes within the problem's constraints. Here, we start by importing the necessary Java utilities and defining our solution class and method. The goal of the method is to maximize the sum of the array after performing up to k negations. First, we sort the array in ascending order using arrays.sort, nums. This ensures that the smallest numbers come first, which is important because flipping negative numbers has the greatest impact on increasing the overall sum. Next, we iterate through the array, and for each negative number, we negate it as long as we still have remaining operations, indicated by k greater than 0. Each time we negate a number, we decrement k to reflect the operation used. This way, we prioritize flipping the smallest negative numbers first, which maximizes the sum incrementally. After handling the negative numbers, we check if k is still greater than 0. If k is odd, it means we have one negation left, so we flip the smallest number in the array. To ensure we find the smallest number, we resort the array and negate the first element. Finally, we calculate the sum of the modified array. This is done using a simple for each loop that adds up all the elements in the array. The resulting sum is then returned as the output of the method. And that completes our implementation of the solution. In this example, we start with the array nums equals -4, -2, 3, and k equals 2. The first step is to sort the array, which arranges the negative numbers at the front. After sorting, the array remains -4, -2, 3. Next, we focus on negating the negative numbers. Starting with the smallest value at index 0, we negate -4 to make it 4, and reduce k by 1, leaving k equals 1. Then, at index 1, we negate -2 to make it 2, and again decrement k by 1, leaving k equals 0. At this point, the array becomes 4, 2, 3, and since k is now 0, no further operations are needed. Finally, we calculate the sum of the array, but we'll see that in a moment. Now, we calculate the sum of the modified array. Adding the elements together, we have 4 plus 2 plus 3, which equals 9. Therefore, the output for this example is 9. Moving on to the second example, we are given nums equals -5, -3, -1, 0, 2, and k equals 4. The first step is to sort the array, which arranges it as -5, -3, -1, 0, 2. Then, we start negating the negative numbers. At index 0, we negate -5 to make it 5, reducing k to 3. At index 1, we negate -3 to make it 3, reducing k to 2. At index 2, we negate -1 to make it 1, reducing k to 1. At this point, we have the array 5, 3, 1, 0, 2, with k equals 1. Since k is still 1, and it's an odd number, we need to negate the smallest number in the array. To do this, we first sort the array again, which rearranges it as 0, 1, 2, 3, 5. The smallest number is 0, so negating it still leaves it as 0, and k becomes 0. With no further operations needed, we now calculate the sum of the array. Adding the elements together, we get 0 plus 1 plus 2 plus 3 plus 5, which equals 11. Therefore, the output for this example is 11. Let's now examine the third example. In this example, we start with nums equals 2, -1, 3, -4, -6, and k equals 3. The first step is to sort the array, which gives us -6, -4, -1, 2, 3. Next, we negate the negative numbers up to k times. At index 0, we negate -6 to make it 6, reducing k to 2. At index 1, we negate -4 to make it 4, reducing k to 1. At index 2, we negate -1 to make it 1, reducing k to 0. At this point, the array becomes 6, 4, 1, 2, 3, and since k is now 0, no further operations are required. Finally, we calculate the sum of the array, which we'll see shortly. To calculate the sum of the modified array, we add the elements together, 6 plus 4 plus 1 plus 2 plus 3, which equals 16. Therefore, the output for this example is 16. With this, we've completed the walkthrough of all three examples, demonstrating the step-by-step process of maximizing the sum of an array after k negations. To analyze the time complexity of this problem, we begin with the sorting operation in step 1. Sorting the array nums is done using Python's sort method, which, based on timsort, operates in O, n asterisk log, n, time, where n represents the size of the array. Next, in step 2, we iterate through the array to negate the negative numbers, up to k times. This is a single traversal of the array, requiring O, n, time. If k remains odd after negating the negatives, we proceed to step 3, where we resort the array to locate the smallest number. This resorting step also takes O, n asterisk log, n, time. Finally, in step 4, summing all the elements of the array involves iterating through the array once, which contributes O, n, time. These steps collectively give us a breakdown of the time complexity for the proposed solution. Now, when we consider the overall time complexity, the dominant operations are the two sorting steps from steps 1 and 3, each contributing O, n asterisk log, n. The iteration in step 2 and the summation in step 4 are linear operations, each requiring O, n, but these are less significant compared to the sorting steps. Therefore, the overall time complexity of this solution is O n asterisk log n. Shifting focus to space complexity, the input array nums is modified in place, meaning no additional storage is needed for the array. However, the sort method in Python uses timsort, which can require up to O n auxiliary space in the worst case. Additionally, a few scalar variables like k and I are used, which consume only O1 space. This breakdown highlights the minimal space requirements of the solution. Considering the overall space complexity, the auxiliary space needed for sorting dominates, leading to an O n space complexity. Comparing this approach to a brute force solution highlights its efficiency. A naive method may apply a single negation in each of the k iterations, repeatedly finding the smallest or most negative element, resulting in O k asterisk n time complexity. This can become very inefficient, especially when k is large. The optimized approach avoids this by sorting the array initially and processing negations based on the sorted order. This reduces the time complexity significantly to O n asterisk log n, making it far more efficient for scenarios involving large values of k. Examining case-based complexity, the best case occurs when k is 0. Here, only the sorting and summation steps are performed, resulting in O n asterisk log n time complexity. In the average case, typical inputs involve both sorting steps and the single loop for negations, which also results in O n asterisk log n overall. The worst case could arise if k is very large, potentially requiring repeated sorting after each negation. However, the proposed solution mitigates this by limiting sorting to at most 2 instances. Mathematically, sorting dominates the complexity with O n asterisk log n, while operations like looping and summation contribute just O n. This keeps the total time complexity bounded by O n asterisk log n. The space complexity remains minimal, as the primary cost is the O n auxiliary space from timsort, resulting in an overall O n space complexity. When solving this problem, there are a few common mistakes that students often make, and addressing these can significantly improve your approach. First, negating random elements without a clear strategy can be a major pitfall. The key is to prioritize the smallest or most negative numbers because flipping these will have the greatest impact on maximizing the sum. Without this prioritization, it's easy to end up with suboptimal results. Another issue is failing to use efficient methods, like sorting or a priority queue, to locate the smallest element. If you iterate through the array repeatedly to find the minimum, you'll likely end up with an O k asterisk n brute force approach, which can be significantly slower than using a min heap or sorting. Lastly, it's critical to handle scenarios where k is larger than the array size. If this edge case is ignored, you might mistakenly assume that negations are always straightforward, but repeated operations on the same elements or cyclic effects need to be carefully considered for correctness. Now, another common oversight is ignoring specific edge cases, such as when the array consists entirely of positive or negative numbers. These scenarios require tailored strategies. For instance, if all numbers are positive, simply negating the smallest values can be counterproductive because it reduces the sum rather than maximizing it. On the other hand, with all negatives, thoughtful negation becomes crucial to make the most significant gains. Additionally, it's important to consider whether k is odd or even after performing all possible negations. If k is odd, the last negation flips the smallest absolute value, which can inadvertently decrease the sum. Recognizing and addressing these nuances will ensure a more robust solution. To succeed in interviews, it's essential to understand the optimal tools and patterns for this problem. Using a min heap or priority queue allows you to efficiently retrieve and modify the smallest element, a common requirement in problems involving repeated operations. This is part of a broader pattern where greedy algorithms, combined with appropriate data structures, help achieve the best results in optimization problems. In interviews, make sure to clarify edge cases, such as when k is greater than the array size, or when the array contains only positives, negatives, or zeros. Also, be ready to discuss time complexity trade-offs. For example, while a brute force approach might be easy to explain, sorting or heap-based solutions are more efficient, with complexities of O n log n or O n plus k asterisk log n, respectively. Demonstrating this awareness can set you apart. This problem is closely related to a few other LeetCode problems, which can help reinforce the underlying concepts. For example, LeetCode 1046, last stone weight, also uses a priority queue to repeatedly modify values for optimization, a very similar approach. LeetCode 621, Task Scheduler, highlights the use of heaps to manage repetitive operations efficiently, which is another useful technique to practice. LeetCode 581, Shortest Unsorted Continuous Subarray, emphasizes sorting and handling edge cases, while LeetCode 1029, Two-City Scheduling, involves a greedy algorithm to carefully balance trade-offs in a sum. Exploring these problems can deepen your understanding of the patterns and strategies involved. When comparing alternative approaches, each method has its own trade-offs. The sorting-based approach involves sorting the array first, then negating the smallest k elements. While this is simple to implement, with a time complexity of n log n for sorting plus k for negations, it may not be the most efficient for large K. A more optimized solution involves using a min heap. By building the heap in n and performing up to k operations in k asterisk log n, this method is faster for larger values of k but requires familiarity with heap operations. Finally, there's the brute force approach, which iteratively finds and negates the smallest element. While straightforward, it is computationally expensive, with a time complexity of k asterisk n, making it impractical for larger inputs. Understanding these trade-offs helps you choose the best method for a given scenario. An alternative perspective involves using mathematical insights to minimize redundant computations. By analyzing the parity of k, you can avoid unnecessary negations that don't contribute to maximizing the sum. For instance, if k is even, all negations cancel out in pairs, whereas an odd k requires careful handling of the last negation to avoid reducing the sum. These insights often lead to solutions that are more efficient than brute force or even sorting-based approaches, sometimes achieving complexities as low as n log n, or better, depending on preprocessing. However, this method requires a deeper understanding of the problem and meticulous handling of edge cases. It's a powerful strategy for advanced problem solvers willing to explore beyond standard approaches. Great job! Today, we learned how sorting and strategic negations can help solve optimization problems like this one. Remember to practice similar questions to strengthen your skills. Thank you for watching, and see you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!